So thank you, Christian, and thank you all for coming. So I will present a study that we done looking at the global warming potential of hydrogen. And this has been part of a research project, a knowledge building project for industry funded by the Research Council of Norway, and also with 5 user partners. And it's been a very nice experience to have these user partners with us, and it has been a lot of good discussions along. And this actually started 3.5 years ago with Equinor contacting us because they wanted to know more about the climate impacts of hydrogen and about what happens when you burn hydrogen and you get water vapor. Is this something to consider? And we then started on a literature review and also then got this project funded. And now we have a paper out, so I will present that, and I will go a little bit into the background and into the details, and then come back to the main conclusion and implications. So today, hydrogen is produced entirely from fossil fuels. So that's the gray and brown hydrogen. But hydrogen is considered one solution to the energy transition that we need to do, and that's then blue and green hydrogen, with green hydrogen produced from renewables and blue hydrogen with CO2 with the fossil fuels, but that CO2 is captured. And they play a key role in future energy scenarios that are compatible with the Paris Agreement targets. But even if you produce hydrogen with almost no emissions of fossil fuels, the green hydrogen, it can still have a climate impact. And that is what I will talk about today. And it has been raised some issues that we don't know that much, or we don't know all the risks to a hydrogen economy because of the hydrogen leakages. So this is what I mean with hydrogen emissions in this sense, is the hydrogen. Because when you burn hydrogen, you only emit water vapor and oxygen. So this is the leakage of hydrogen that happens during production and transport and end use. So a little bit on the hydrogen budget. When hydrogen is emitted into the air, it actually stays in the atmosphere for 2 years. So it gets transported around the world and get quite well mixed. It has very different sources outlined here in blue. So that's from fossil fuels, and these numbers are based on a CO proxy. And then you have biomass burning, and you have some nitrogen fixation, and hydrogen is also produced chemically in the air, but it's photooxidation. You also have some studies pointing out that you could have some natural geological sources, but as you can see on these numbers, it's quite uncertain how large this source is. So the concentration of hydrogen is currently 530 ppb. It has been rising steadily since the Industrial Revolution because of the fossil fuels emissions and the chemical production in the air where methane is involved. You have mainly 2 sinks, so that's in the brown. You have the soil uptake, which is the largest, so it's bacteria in the soils that take up hydrogen. And that's also the largest uncertainty in the hydrogen budget. And then you have the OH sink. And the OH sink is important. So that's how hydrogen is chemically removed from the atmosphere. And this is why hydrogen has a climate effect. So we can go into that. This is the main impact of hydrogen into the atmosphere. It has a lot more chemistry than this, but this is hopefully simplified, but I will go through it. So as you can see in the big big reaction in the middle here, where hydrogen reacts with OH. This is the zinc, as I said, and OH is an oxidant in the atmosphere. It reacts very rapidly with other gases. It actually stays just 1 second in the atmosphere, but it does a lot. So it swipes through. It's kind of like a vacuum cleaner. So it swipes through and removes a lot of other gases. Hydrogen is one gas that it removes, and methane is another. So, and that's the equation to the left. And then you see that when you put in more hydrogen, the OH gets then busy removing hydrogen, you can say, and then you will get the pileup of methane. You will then get increased methane levels and increased methane lifetime. And methane is an important greenhouse gas. You will also get, via some other reactions, including NOx, to have then ozone. So you will also have then increased ozone in the troposphere. So that's, well, the lower, in the lower troposphere where we live, this is considered a toxic gas, and it's a greenhouse gas. This can also influence in the stratosphere, so that's higher up where, or above where airplanes go. You can have changes in the ozone layer there, and also water vapor. So as I said in the start, water vapor, so Equinor was concerned about the water vapor production. And near the surface, there's so much water vapor, so it doesn't matter if you add a little bit more. But high up in the stratosphere, it's very dry, cold, and when you have this increased production of water vapor there, then it can have an impact. And water vapor is a greenhouse gas, so then it also leads to global warming. So it's important to take all these effects into account when we want to calculate the global warming potential of hydrogen, because all of these gases contribute. So you call hydrogen an indirect greenhouse gas, changes methane and ozone and stratospheric water vapor. So what we did in the study is that we used 6 global atmospheric chemistry models. 5 of them were used for the perturbation. And then, so this, we had a model in Oslo, but then we went to have experts in the UK and France and in US that also run models. And it's important to run different models because then we could get, I mean, single model studies are very important, but it's important to have more of them. So you can compare the models, and then we could get a better estimate of the uncertainty because these models are quite different. With the chemistry, they are quite detailed. So these are 3D global atmospheric chemistry models. So you have the latitudinal and longitudinal grid, and then you have then calculations of tracers and hydrogen gets transported around in the troposphere and stratosphere. And then you have some complex chemistry then. So we could then add hydrogen into the surface layer and then see how this affected other gases in the atmosphere. So coming back to the chemistry again. So here I'll just say add what we saw in the models and compare. And the models actually agreed quite well. So if you first go into the methane, this is a very complex unit, so don't mind that, but that's the radiative forcing, the effective radiative forcing on methane, and it's then normalized by the hydrogen flux that we added. So as you can see, the models agree quite well. The models with the EMI is the emission-driven models. So we had some different setups of the models too to test if this had an influence. But they agree quite well. So we see an increased methane lifetime levels. And we also saw that the ozone increased. So this is the total ozone per hydrogen flux. We didn't see that much. So this is the total ozone, the total column. We didn't see that much in the stratosphere. Some studies have found bigger increase in the or decrease in the ozone layer, but we didn't find any significant changes there. So this ozone, most of this ozone is in the troposphere. And then the stratospheric water vapor. All the models assume an increase also there. You can see a bit larger spread, and also one model were not able to calculate this. A final thing that we looked at particles, aerosols, because the oxidants also changes this, especially from sulfur gas going into the sulfate aerosols. But this was not, as you can see, the models didn't quite agree, and it was not something that we looked more into, but it's certainly something maybe to have as a to look more into. But yeah, we didn't see much of a change there. So just to since this, so we have all on the same page here, the global warming potential that we wanted to calculate in this study. This is a metric that allows a comparison of the global warming impacts of different gases. So the gases, they differ by their ability to absorb energy and also how long the gases stays in the atmosphere. So this metric takes this into account. It compares then 1 ton of a gas, so here hydrogen, to 1 ton of CO2, and then over a given time. So the 100-year time is the most common to use. And we wanted to calculate this because it's not, for instance, reported in IPCC because it's not enough data to report here. And then, so just to clear up a misunderstanding, if you say that, as we stated in the press release, that hydrogen is 12 times larger than CO2, it says that the global warming potential is that high, and that's for emission. So 1 ton emissions of hydrogen versus 1 ton or kilo then both of CO2. It does not say that hydrogen is 12 times worse than fossil fuel, just to make that clear. And also, for instance, methane has a global warming potential of 28 to 30. So it's then, and CO2 has then 1 because it's the reference. So that's our conclusion. So we did then calculate global warming potential over 100 years with hydrogen. And then here you see the model results. And we were able then to split between methane, as you see in well, turquoise color, and yellow in ozone. So they contribute most. And then you have a 20% circa for stratospheric water vapor. And then we also have, for the model mean here, you see also a range. We spend a lot of time on this uncertainty range. That's 1 standard deviation based on the models that we have, the individual models, but also literature. And if we compare to the previous data or literature that is published, so there is a paper by Warwick coming, and now it's in the discussion phase. And it was based on a report that came last year with a bit lower number, but this is 12, and a 90% confidence interval of 6. And then we have another paper, Hagelstein, that has 12.8. So that's also within our results. It's twice as high or more than the pioneer work that Derwent made several papers. But he used different models, so 2D model, and not including the stratospheric impact. So the global warming potential of hydrogen, you can say it's 12 based on this. So what are the implications? So our estimated global warming potential, 100 of hydrogen is then 39% of fossil fuel methane. So it's not zero, and but it's better than methane, you could say, and then 12 times more than CO2. And hydrogen leakages will lead to global warming. So it will be very important to keep hydrogen leakages at a minimum to then accomplish the benefits of switching to a hydrogen economy. Because, I mean, the potential benefits of switching to a hydrogen economy will, of course, depend on how large these leakage rates are, but also what it replaces. So if it replaces a very carbon-intensive sector, then it can, of course, have a large potential in reducing CO2 emissions. So, but how large are these leakages? This is not something that we have looked at in this study, but I thought I just have a slide at the end. This is a very nice literature review by researchers at Columbia University and Energy Policy Group. And they conclude that there's very little data on hydrogen leakages along the existing value chain. And the one that which does exist, it comes from theoretical assessments, simulations, or extrapolation rather than measurements from operations. And this is important that we don't know how large or small these leakages are. They do, based on literature review, they do. This is just part of the table. I just thought I'd show from green, blue, and gray, blue, and green hydrogen. They, in green here is the 2050, they model a high leakage scenario based on literature. So this is they split between production and delivery and end use. And as you can see here, so the high leakage rate, they assume that the leakage rates are as today. And then for the low leakage rate, on the right here, they assume that there are technical developments in reducing the rates. So green hydrogen is higher than blue and gray. So this also changes how the leakages will look like in the future, because we know little about what they look like today, and then even less what they will look like in the future. But they do try. So this is a figure again from their review, where they look at both in tons and percentage how this can look like in 2020 and 2050, with then leakage rates going from 2.9% to 5.6% if the leakage rates are as today. Split then again between the production and the delivery phase, which we know a little bit more than the end use leakage rate, which we know even less. So there is a high need to monitor and start these leakages, and also to get equipment. The leakage of hydrogen that has been today is mostly from safety issues, and they don't have the lower the lower values to calculate the smaller leakage rates that occur. And with that, I say thank you. So this is the paper that we published, and you can read more there.